Okay, so today we're going to be going over discussion 2-1, spectral analysis of atomic structure. So basically what we're going to be looking at here is the physical evidence for the structure of atoms that we're going to determine looking at a variety of spectra. Spectra include the mass spectrum, emission spectra, and continuous spectra, both of which we looked at in IB Chem 1, as well as an absorption spectrum. All right, so first let's start with the mass spectrometer. Well, what happens in the mass spectrometer? So a sample is inserted into the mass spectrometer, and the atoms or molecules in the sample are vaporized and ionized. They then get accelerated and separated by electromagnets based on the mass to charge ratio, where the heavier portions of the sample are deflected less than the lighter portion of the sample. So what you see is in the spectrum is a series of peaks. The x-axis will show the mass to charge ratio, and the height of each peak will show the relative abundance. Now you probably remember from IB Chem 1, the formula for calculating the average atomic mass for an element is the mass of the first isotope times its decimal percentage, plus the mass of the second isotope plus times its decimal percentage, plus ... for however many isotopes you have. So here is a mass spectrum of rubidium. Right, so if you look at that mass spectrum, you see that rubidium has two isotopes, one with a mass of 85 and one with a mass of 87. We see that the isotope with a mass of 85 is more abundant than the isotope with a mass of 87. So in order to calculate the average atomic mass for rubidium, the first thing we have to do is measure the peak height. Once you have the height of the peaks, you can use those heights to calculate the abundance. So to do that, we will plug into the average atomic mass formula, multiply 85 times the height of the peak representing the mass of 85 divided by the total height of both peaks combined, plus 87 times the height of its peak divided by the total. So take a moment, pause the video, and see if you can do that for yourself. Okay, so when we do that, to me it looks, I just kind of eyeballed it, and it looks like the peak for 85 is about twice as big as the peak for 87. So the total height of both the peaks combined, I'll call 1.5. So I multiply the mass of the isotope with the mass of 85, times 1 divided by 1.5. Plus, I'm sorry, that should be a plus sign, 87 times 0.5 divided by 1.5, and I get an average atomic mass of 85.67. Now, that is not perfect. So if you look at the periodic table, the average atomic mass of rubidium is 85.47. But if you had to use that mass spectrum to identify the element, no other element would come closer than rubidium. Excuse me. This is the first time I've done this, so you're going to have to bear with me. All right, so what is relative atomic mass? So we can't really measure the masses of individual atoms very easily because individual atoms are very, very tiny. We cannot isolate them, and even if you could, you can't put an atom on a balance and get a reading. So they derive the mass using a unitless quantity that is relative to some standard, and that standard is an atom of carbon-12. All right, so they essentially just they calculate the relative atomic mass by dividing the mass of one atom of the element by 1/12 the mass of carbon-12. Now, generally they don't ask you to calculate relative atomic mass because you could just look at it on the periodic table. But you do need to know that carbon-12 is the standard that is used for deriving those masses. Now, how does that correspond to what you see on the periodic table? Well, by now we all know that the mass for each element on the periodic table is the relative atomic mass in grams per mole. So it's essentially the same. We just use a different unit. So the electromagnetic spectrum. If you look at the electromagnetic spectrum, you can see at the lower energy end of the spectrum, the radiation is in the form of radio waves. As you move from lower energy to higher energy, you see that radio becomes microwave, and then infrared radiation. That narrow band in the middle is visible radiation, so we can see that red light has a lower energy than does blue or violet light. After visible light, you see ultraviolet, and then X-ray, and then gamma. Now, if we look at the lower energy end of the spectrum, as we move toward the higher energy end of the spectrum, we see that the wavelength of radiation is decreasing. Now, if we look at the frequency, because the wavelength is decreasing, the frequency of the radiation also increases from the lowest energy to the highest energy. Okay, so summing up, the smaller the wavelength, the higher the frequency, and the more energy the radiation will possess. That is why infrared radiation we feel is heat, and ultraviolet radiation will give you a sunburn because it has more energy than does infrared. Okay, so we can do calculations with energy according to this equation. E equals h nu, which also equals hc divided by lambda. Now, the terms in here in this equation, E is the energy of radiation, H is Planck's constant, which is 6.63 times 10 to the negative 34th. Nu, or the letter that looks like a V, is the frequency of radiation. And C, is the speed of light in meters per second. That's 3.0 times 10 to the 8th meters per second. And lambda is the wavelength of radiation. Now, you do not have to memorize Planck's constant or the speed of light. Both of those values are given to you in the data booklet. So basically, if you know the frequency of the radiation, you can calculate the energy. If you know the wavelength, you can calculate the frequency, or you can calculate the energy, etc., etc. Basically, these are just plug and chug problems. So let's look at the first one. What is the energy of light with a frequency of 10 to the 8th per seconds, or seconds to the minus 1? So take a moment and determine which portion of the formula you need, and go ahead and do your plugging and chugging. So pause the video, and I'll put up the answer in a second. Okay, so just like I said, we're going to do h times nu here, Planck's constant times the frequency, which is 6.63 times 10 to the negative 34th joule times seconds, times 10 to the 8th seconds to the minus 1. When you put that in your calculator, you should get 6.63 times 10 to the negative 26 joules. Alright, so that was an example looking at with a given frequency. Now let's do an example with a given wavelength. Now this is a little bit more complicated because we're going to take Planck's constant, multiply by the speed of light, which is in meters per second, and divide by the wavelength, which is in nanometers. So before you do that conversion, before you plug in the numbers, you have to convert nanometers into meters so that the units cancel out appropriately. So make sure you go ahead and do that, and I will give you the answer in a second. Okay, so now we're going to use the portion of the equation that concerns wavelength, and we're going to multiply Planck's constant times the speed of light divided by the wavelength. Now you'll see here that I converted the wavelength in nanometers to meters basically just by putting a times 10 to the minus 9th meters at the end of 700, because a nanometer is 1/billionth of a meter, or 10 to the negative 9th meters. And when you plug those numbers into your calculator, you'll get 2.84 times 10 to the negative 19th joules. All right, the continuous spectrum. So a continuous spectrum is produced when light passes through a prism. And it's essentially a rainbow. When you look at the continuous spectrum, all we see is one color smoothly bleeding into the next with no breaks or divisions. So the spectrum contains all the wavelengths of visible light. Now, emission spectrum is a little bit different. When energy is supplied to an individual element, they will emit a spectrum which will only contain emissions at particular wavelengths. That means that what you will see is a mostly black background with individual lines of color. Now, each element has its own characteristic spectrum, so by looking at an emission spectrum for an element, we can actually compare it to the known spectra and determine what the element is. So there's a spectrum for hydrogen. Now, when energy is supplied to an atom, it doesn't matter if that is electrical energy or heat energy, the electrons become excited. In other words, they absorb that energy, which causes them to move from the lowest possible state, called the ground state, to what is known as an excited state. Now, when those electrons drop back down from the higher energy level to the lower energy level, they will emit the energy that they had absorbed in the form of electromagnetic radiation. Now, that specific wavelength of radiation will show up as a line in the spectrum. Now, the significance of this. This tells us that only certain energies are allowed or possible for the electron in a hydrogen atom. In other words, the electron can only move to a specific point or a specific energy level in the atom. Now, if in contrast, if electrons were allowed to go wherever they wanted, then what we would actually see is a continuous spectrum. All right, so convergence. Now, look at the spectrum we have here. Notice that as we move from the lower energy end of the spectrum to the higher energy end of the spectrum, the lines become closer together, or they converge. All right, now, why does this happen? Well, in real life, atoms, the energy levels in atoms actually do converge as you get farther away from the nucleus. As the circumference of the atom increases, the energy levels can become closer and closer together because less energy is required to promote electron to a more excited state. Okay, so energy level transitions. Now, before I go into this, actually, I will do this. I'm trying to figure out the order that I want to do this. Okay, so when electrons are excited and then return all the way back to the first energy level, the series of lines that will occur in the spectrum will show up in the ultraviolet end of the spectrum because that involves the largest possible energy change. Now, the distance the electron travels from the nucleus the further an electron travels, the greater the distance, the greater energy that represents. Okay? So again, if the electron transition ends at n equals 1, we call that the Lyman series, and the lines will appear in the ultraviolet region of the spectrum. Now, if we transition to n equals 2, it's known as the Balmer series, and the lines in the spectrum will appear in the visible region. And you will still get a little bit in the UV, but most of the lines will be in the visible spectrum. And transitions that end at n equals 3 are known as the Paschen series, and they will appear in the infrared region. So it's important to note, you don't really need to know the names of the series, but you do need to know what type of radiation would be emitted if an electron landed in a certain spot. So let's actually look at this real quick. Oops. Okay. So one thing you guys are required to do in this course is to draw energy level diagrams. So to draw energy level diagrams, we represent each energy level as a horizontal line. So there's one energy level. I'll draw another parallel line to make the second energy level. Other parallel line to make the third. Notice I drew the third line closer to the second line than I did the first line. And the fourth line is even closer still to the third line. All I'm doing here is showing convergence. You got to make sure that you show convergence. Now the final line is farther away than all the rest. All right, so let's label them. So the first energy level we'll call n equals 1. The lowercase n is used to denote an energy level. So the second one we'll call n equals 2. N equals 3, n equals 4, etc. And then the last one up here we will call n equals infinity. So here we go. Yeah, infinity. Okay, so for a hydrogen atom, the ground state for any for the lone electron in the hydrogen atom is n equals 1. So if we zap this atom with energy, whoop, the electron will be promoted to a higher energy level. So now it's at n equals 4. Now, the electron could fall all the way back to n equals 1, it could fall to n equals 2, or it could fall to n equals 3. So what they ask you to do, the way you'll see these questions asked, it'll say, show a series of lines that would result in ultraviolet radiation. So we know that for an atom to emit ultraviolet radiation, when the electron travels back down, it has to travel all the way back to n equals 1. Okay, now when you're looking at a sample of hydrogen, there's more than one atom in the sample. In fact, there's a whole bunch of atoms in the sample. So some of the atoms will have that electron that goes to n equals 4 terminate. Oh, actually, that's not what I want to do. I'm sorry. Now, some of the atoms, will have the electrons promoted to n equals 3 as opposed to n equals 2. So the electron that goes from n equals 3, if it was going to produce ultraviolet light, would have to go all the way back to n equals 1. Now you could also have an electron promoted to n equals 2, which would also go back to n equals 1. Now, all three of these electron transitions will produce ultraviolet light because they all terminate at n equals 1. And what we have here is the series of lines that would produce ultraviolet light for the hydrogen emission spectrum. Now we notice here n equals infinity. So if an electron in the ground state absorbs enough energy to go all the way up to n equals infinity, it reaches what is known as its convergence limit. Now the convergence limit basically just represents the amount of energy required to ionize the atom. In other words, an electron that makes it all the way to n equals infinity will actually be removed from the atom and create a cation. Okay, so there's a little preview. Okay, so here is a problem calculating ionization energy. Now this might look a little bit different than the other energy calculations we did, but I guarantee you it's the same exact thing. So let's read this. It says in a given atom, it is said that an atom is ionized when it reaches its convergence limit, or n equals infinity. In looking at lines in a Lyman series, this would be the line with the shortest wavelength. In other words, the highest possible energy, which is n equals infinity to n equals 1. So here's the question. It says for a particular atom, the shortest wavelength line in the Lyman series is 91.16 nanometers. Calculate the first ionization energy of this atom. Now, those words, shortest wavelength line, are pretty much the indication to you that we are calculating the energy of the convergence limit, right? So again, all we do is plug into our equation for calculating the energy of radiation. We're given a wavelength, so we're going to use hc over lambda. And when we plug in the numbers, we do Planck's constant times the speed of light divided by the wavelength in meters. Don't forget to convert nanometers into meters. And when we do our calculation, we get 2.18 times 10 to the negative 18th joules per atom. Now, we don't generally see ionization energy as joules per atom. We see it as kilojoules per mole. So to do that, we are just going to convert joules per atom by first converting joules into kilojoules, and then we will convert atoms into moles. And we get 1.31 times 10 to the third kilojoules per mole. Okay, so finally, absorption spectra, how it works. So when light is passed through a gas, some wavelengths of light of that light will be absorbed by the gas while others pass right through. So when you look at an absorption spectrum, what you see is sort of a continuous spectrum with individual black lines going through it. Now the dark lines represent wavelengths of light that have been absorbed by the gas, and different gases will produce different absorption spectra. So the uses for this are many. Now most colored things will have an absorption spectra. They'll absorb specific colors of light and transmit others. For example, leaves and grass are green, right, because they will absorb all the wavelengths of light, but they reflect green. Right? Another really good use is analyzing the atmospheres of exoplanets. So exoplanets are planets that orbit stars other than the sun. And when those planets pass in front of their mother star, if they're aligned correctly with Earth, the light from that star will pass through the atmosphere of the planet, and that light will eventually reach Earth. Now, we can actually analyze that light to determine the composition of that atmosphere, and that is really at the forefront of astronomy now. And that's all we have for discussion 2-1. That was my first podcast. I promise they'll get smoother as we go along. Ari, do you have anything to say to my students?
What?
Do you have anything you want to say to my students?
That's all, folks.
All right. See you guys.